Okay, so last week we concluded our discussion of calculating state changes and using balances. So how we started the class off and how most undergraduate chemical engineering, at least the first semester, depends, a lot of schools teach thermal quite a bit differently. Some places will have multiple semesters, some will have just one. So what we talked about was combining balances with state changes. And for this, the balances we're talking where we said du dt is equal to summation of enthalpy entering the system. We could have heat, we could have shaft work, and we could have PV expansion of the system. Right, this is our general energy balance equation. For a closed system, we get rid of this term. For an adiabatic system, we get rid of the heat. If there's no turbine or impeller or a pump, we don't have any shaft work. If it's got rigid walls, we don't have any PV volume expansion work, like a balloon. If it's steady state, the total energy in the system doesn't change as a function of time. So this system here is just any process that we can basically draw a box around, or a loop, or any sort of oddly shaped defined boundary. We also have the entropy balance, where we're adding up all of the entropy flowing into the system or flowing out of the system. Entropy is a extensive property, so mass or moles carry with it entropy. Entropy can flow in and out of the system in the form of heat. Right? We generate entropy based on having a mismatch at which one system loses energy at a certain temperature, from which another system gains entropy at a certain temperature. And that was the example for the homework problem where we looked at the heat exchanger. When you ran the hot gas at 1,000 degrees C, you generated a certain amount of entropy. When you ran it at 2,000 degrees C, you generated even more entropy. So when you use a higher temperature difference, or higher pressure difference, or higher concentration difference to drive a process, you can accomplish that process more quickly, but you ultimately end up throwing away work. When you generate entropy, you lose the ability to use that energy in some other reversible process. And then we have the entropy generation. Now, how we solve all problems basically for processes is then we combine this information with the expressions that we derived for changes in internal energy, changes in enthalpy, changes in entropy, and so on. Right? We typically expand this with respect to temperature and volume, temperature and pressure, and with entropy we can expand it with respect to a lot of different variables. Entropy is relatively straightforward to manipulate. So if then we take an equation of state and we plug it into each of these three relationships, it gives us tremendous predictive power of the properties of fluids. And so where we ended off last week, if we have an equation of state plus heat capacity, and I'll say etc., there's a couple other properties we have to measure. Maybe the heat of vaporization, maybe the density. Well, I'm not sure actually the equation of state predicts the density. But with a very limited subset of material properties, plus a relationship of how temperature, pressure, and specific volume interact, we can basically figure out all of the thermodynamic properties of matter. With this information, we plug it into our balance equation. Our balance equation is how we interact with the thermodynamic world. We can interact with the system by adding heat or taking away heat, by adding work or extracting work, right? You can add work by having an impeller, like a mixer, or a blade for a pump, or we can expand the fluid very carefully using a turbine, or we can just physically constrict or expand the system like a classic piston cylinder device. So this is how we interact with the thermodynamic world. All of these relationships here, which are for the state changes, these are just keeping track so we don't violate the first and second law of thermodynamics. So combining our interaction with the rules of physical properties of material in the systems, that basically allows us to solve any real process that we care about. If we all had access to the equivalent of steam tables, but for absolutely everything in the world, then it would be super trivial to solve all problems. We would just have to go to the table, look up what's the temperature and pressure, read off all the properties, plug it into the flow rate, and we'd be done. But that's not the case. We're going to be dealing with systems where we're going to say it's a reversible process that's adiabatic. So if it's reversible, this goes to 0. If it's adiabatic, this goes to 0. If it's steady state, this goes to 0, which tells us that the entropy in has to go to the entropy out. We take that knowledge, we then say ds has to equal to 0, and based on whatever we expanded it with, let's say temperature and pressure, then we can derive a relationship for how the pressure and temperature have to follow a very set definite curve that allows us to run the process isentropically. So there's a lot of different things that we can do with these simple relationships. And for the most part, an undergraduate thermodynamics class, we would spend weeks and weeks and months going through all those different details, talking about how PT relates for a polytropic process, for a isentropic process, for an isothermal process, all these different things. But we have the tools and the power now to figure it out as we go. Right? So the main thing is you want to be very comfortable on how to use these relationships, and we'll spend a lot of time talking about these ones here. But you want to be very comfortable on how to use all of these different terms, because I may throw you something on an exam or a quiz that you've never seen before. But knowing that the first step, when you see a balance, do an energy balance, do an entropy balance. Then when you don't know what your H's and your S's or your U's or your S's are, then we expand and go to these different relationships here and figure out how to figure out those what they are. All right, so that's it for that portion of the class. Done with balances. Now we're moving on to phase equilibria. This is where we'll be spending most of our time. Phase equilibria. Now, what we're talking about here is if I have two fluids in contact, how do I know that they're at equilibrium? Because if I know that they're at equilibrium, then I can read off specific properties associated with it. Most specifically, as chemical engineers, we care about the composition. So if I have a multi-component, multi-phase mixture, right, a flash calculation is a classic example. Theoretically, a flash calculation is fairly advanced. But usually when you come to an undergraduate thermodynamics class, you'll tackle flash calculations very soon on when you start talking about phase equilibria, because students want to see the application. They want to know how you can actually solve real problems. We're going to do it the slow and boring way, where we're going to go through very simple systems and then work our way up to complex systems. So most of us have seen a flash calculation. Who's seen a flash calculation? Where we have a liquid flowing in, we have a vapor flowing out, and we have a liquid flowing in. Now this has a total composition, Z of I, meaning total molar composition, I being all the individual species. The bottom stream we typically denote it as X, the top stream we typically denote as Y. These are the mole fractions of the vapor, mole fractions of the liquid. And we use what we call Raoult's law, R-A-O-S law, where we can relate the molar composition of the liquid using the saturation pressure to the molar composition of the vapor phase. And this has to be satisfied for every species active system. So this is very useful, and this is the stepping stone to moving into distillation columns and more advanced separation techniques. Phase equilibrium is the one area that chemical engineers more or less have completely cornered. There really aren't any other disciplines that do phase equilibrium calculations. A lot of disciplines will apply energy balances and entropy balances to solve processes, but when it comes to separations and phase equilibrium and reaction equilibrium, chemical engineers more or less have it cornered. Chemistry disciplines and physical chemistry disciplines focus a lot, but they more so work on closed systems. So if you do an open system with phase transitions, for a real representative process in a refinery, for example, or a chemical plant, that's where chemical engineers have our strong area. So what we're going to be doing is, over the course of a while, eventually getting to deriving Raoult's law. Right? So we're going to derive Raoult's law not from sort of applying it and then talking about what we can learn from it, but instead we're going to derive the equivalent of Raoult's law, but for a real fluid. This is for a very idealized fluid. This assumes ideal mixing, this assumes ideal gas behavior. There are a lot of assumptions that are baked into this relationship here. So we're going to derive everything for a real fluid, fundamental thermodynamics, and then we're going to simplify it down so we're aware of all of the assumptions that we're making to get to this point right here to solve this solve this flash problem. So the first step is we have to determine, how do we even know that two fluids are in equilibrium? How do we then even start to develop a relationship? So first we're going to derive the equilibrium criteria. So again, we're going to arbitrarily define a system, but of course the system is going to be defined in a way that we can extract meaningful results. So this is going to be an isolated constant volume system where there's not going to be any change of the system size, there's not going to be any exchange with the environment. So this is basically the universe according to this derivation. And we're going to break this into two chambers, chamber 1, chamber 2. And I have a perforated line because basically we can exchange mass, we can exchange volume, we can exchange energy across this boundary. So on each side, we're going to have a number of moles, we're going to have an entropy, we're going to have an internal energy, and we're going to have a volume of that chamber size. Same thing on side 2, or we can call it phase 2, assume we'll figure out. 2, entropy, internal energy, and volume. These are all of the properties of thermodynamics that we've talked about, right? The three fundamental variables, entropy, internal energy, and volume, but we're also including moles or mass as well. So this is the entire universe, and according to thermodynamics, this is all we need to define all of the properties of the system. So if we can find a relationship between the left-hand side chamber and the right-hand side chamber, then we know how the entropy, internal energy, and the volume all have to interact with one another to ensure that we're in equilibrium. So if we jump forward, we could say this is liquid and this is vapor. So how do we know that this is a saturated liquid and this is a saturated vapor? What relationships can we develop between these variables that allow us to know we've reached that point? So equilibrium is obtained when we have the rate of change of entropy is equal to 0. Now this is going to be the case for most everything, right? For everything. So when we're at equilibrium, everything has to be time invariant. Time invariant. The enthalpy can't change, the Gibbs can't change, the entropy, internal energy, the volume, everything has to be static. But we're going to use the entropy because it has some additional criteria here that we also know that the curvature of entropy is concave. And so as a reminder, what we mean by the entropy being concave is that if we were to ever look at a plot of the entropy as a function of any variable, this could be time, this could be temperature, this could be pressure, it could be whatever variable we want. If entropy were to look like this, the only position on this curve that we could say was in any sort of a pseudo-equilibrium state would have to be right here, meaning that it's an invariant, it's at a constant, it's a flat position. But if we were to take a system that's at exactly this state, and there were to be some slight perturbation to occur, and it would split into two different systems, one with slightly different entropy going in each direction. Right? And then you can imagine this as having just two molecules, and you would pull them apart a little bit or rotate one of the other molecules. Right? One of the entropies may change of one system, and one might change the other way. The combined entropy of the system is higher in a convex shape. And in fact, this is true regardless of where we're at in the curve. Right? If you combine those two values of the entropy, they're always going to be higher. which means that if you have a system where the entropy is convex like this, any slight change, no matter how infinitesimally small, will increase the entropy, and basically the whole universe will explode. Right? Because everything would cascade and increase the entropy. Every move, every change in position, every change in temperature, every change in pressure would be something that would increase the system's entropy. Alternatively, if we have entropy as a concave function, and this were to be our equilibrium point, if we were to split into two systems of different of different entropies, it would always lower the entropy and it would want to come back and stabilize the system. Right? So the curvature of entropy is equally as a fundamental component to the second law of thermodynamics as all the other characteristics here. And we're going to apply this stability criteria later on to actually derive some additional relationships. Okay. So what we're saying is that this system right here, we are going to say that it's at equilibrium when the total entropy rate of change is equal to 0. The variables that we're interested in are all these four ones here. So we're going to do what we've done previously, is we're going to expand entropy with respect to the other three variables, U, V, and N. Very similar derivation approach we've done before. Now I'll write this out for side 1, noting that we can do exactly the same thing with side 2. Oops. Holding V and N constant. And so we can actually do exactly the same thing, but just swap all the 1s for 2s, and it looks exactly the same. So what we're going to do is this expression here, the change of entropy with respect to changes in internal energy with the volume equal constant, this is just equal to the reciprocal of the temperature of that side of the chamber. Similarly, I don't think we explicitly derived this equation in class, but we can derive this. It's on your useful relationship equation sheet that's in the Sandler book. This expression here is exactly equal to Gibbs over temperature. And then lastly, this expression here, we're going to manipulate with the triple product rule. So with the triple product rule, I always have to take a moment and re-remember how to do all this. So we just rotate, I think in a counterclockwise fashion. That's right, ds, dv. Let's rotate again, change the volume. This one, okay. And keep this. So this is the variable we're trying to figure out what it's equal to. This is just equal to the temperature. And this is equal to 1 over the pressure. Right? Change in internal energy with respect to changes in volume, that's what the pressure is. Right? If I'm giving or taking away energy from the system, basically that's the definition, so this is the reciprocal. So then this expression here would be equal to minus temperature, minus pressure over double check, make sure I'm not screwing this up. Yeah, pressure over temperature. Oh, my bad, this is minus. That's why. Okay. Pressure over temperature. Okay. So, if we combine these two together and look at the total change of entropy of the entire system, this is equal to the change of side 1 in entropy plus the change in side 2 of the entropy. We can write out a big, fantastic long equation. So as a reminder, what we do when we're playing around with this kind of mathematics here is we're just trying to keep track, right? The goal of what we're trying to accomplish here in thermodynamics with state changes is based on effectively the Gibbs phase rule and noting that we only have 3 fundamental intensive variables of the units, 4 if you include molar or mass properties. All we're trying to do is say we're going to keep track of all of the changes in entropy as a function of all of the other 3 variables. And so we've accomplished that for one chamber here, where we've kind of combined this with our first and second law to give us useful expressions and more or less definitions of temperature and pressure. And then we're just keeping track of all of the different ways that entropy can change in the system. By mass going to chamber 1, mass going to chamber 2, the volume changing between chambers 1 and 2, and the internal energy being exchanged between chambers 1 and 2. We're going to come to them as phases. So for this system, the total change in the number of moles, which is the change in chamber 1 plus the change in chamber 2, has to be equal to 0. There is no exchange with the system to outside of the universe. Right? The total number of moles in our universe here has to be held constant. Same thing with the volume. And same thing with the total amount of energy. So from these relationships, we can show that all of the mass that is gained by chamber 1 is lost by chamber 2. All of the volume that is gained by chamber 1 is lost by chamber 2. And all of the energy that is gained by chamber 1 is lost by chamber 2 or phase 2. So we take this all, put it together. We can substitute all of these relationships here to reduce the dimensionality of our equation so we don't have to worry about so many variables. Basically substitute in these expressions up here. The rate of change of entropy at equilibrium is equal to 0. And then this is equal to So the only unbiased way that we can be 100% positive that the rate of change in entropy is always going to be 0 is if each of these 3 terms are all 0 independently. And from this we derive 3 criteria for equilibrium. Criteria 1 is thermal equilibrium. In order for these 2 chambers to be truly in equilibrium, their temperatures must be exactly the same. Right? Not their internal energies. The internal energy doesn't have to be the same. The temperature has to be the same. Criteria 2 is mechanical equilibrium. That the pressure across both of the 2 chambers have to be in equilibrium. They have to be pushing against each other exactly the same so that the volume is not being exchanged between one system to the other. And lastly, which is the trickiest one, is chemical equilibrium. In this case, the Gibbs free energies of the 2 phases have to be equal to one another. This is also, we'll call this as ds du. So this is the change in entropy with respect to internal energy. This is the change in entropy with respect to volume. And this is the change in entropy with respect to the number of moles in the system. Just as a reminder of our starting point right here, looking at the 3 different variables. So we kind of hold these 2 equilibrium criteria as kind of known facts a lot of time in chemical engineering. We say, oh, at a phase change, the temperature and pressure have to be constant. Most of the difficult work here is ensuring that the Gibbs free energies across the 2 phases are constant with one another as well. So that's the one we're going to spend most all of our time on. So the next step is we don't really like working with entropy very much. So instead, we're going to demonstrate using Gibbs free energy that we can come up with phase equilibrium criteria by minimizing the Gibbs free energy. In fact, you know what? I'll just do the shorthand version of this actually. We can go through more advanced arithmetic, but more or less, if we define Gibbs as the enthalpy minus the entropy times by the temperature, if this is a max, then this has to be a minimum. We can go through a lot of arithmetic to demonstrate that, but I think it's a fairly straightforward concept to interpret. Same thing with Helmholtz. Helmholtz energy is a minimum. So we can minimize the Gibbs or minimize the Helmholtz, and that's accomplishing the same task as maximizing the entropy. We've got some other stuff to cover with our time in class. Okay, questions about equilibrium criteria. So we have made absolutely no assumptions about what we're talking about here. All we have basically said is this could be any arbitrary system with any number of moles, any entropy, any internal energy, any specific volume or any volume. Same thing on the other chamber. This could be a solid, this could be a liquid, this could be a liquid, this could be a vapor. We have made no assumptions. The only simplification that we've done so far is we have basically assumed that this is a single component system. When we get to multi-component systems, we're going to have to repeat this process more or less, but for a slightly different formulation of how we write everything out. Because for a multi-component system, right, it changes how we keep track of these different properties. All right. So I am not going to go through a full derivation here. I'm going to set up a derivation to demonstrate that we can use this stability criteria of the universe to demonstrate a couple of more very key, important, critical properties about thermodynamics. So what we just demonstrated is at equilibrium, the rate of change of entropy, which is equal to the change of chamber 1 plus the change of chamber 2, is going to be equal to 0. For all real systems, though, this is going to be greater than or equal to 0 for any real process. And we also know that entropy has to have a concave function. Is a concave function with respect to all variables. So the same approach that we took to use this criteria to develop our equilibrium relationships, where we expanded the change in entropy with respect to U, V, and N, the internal energy, the volume, and the number of moles, is we're going to repeat that process twice. So whereas we expanded it here once, we had 1, 2, 3, 4, 5, 6 terms when we compared it to D with chamber 2, right? Yeah, here's all of our 6 fantastic terms. Now we get to do this again. So we're going to have 18 terms. So that's why I'm not going to go through derivation, because it's very tedious, and the conclusion is not that hard to interpret. So if we repeat this process, right, where we expand, in this case, just an example, expand the rate of change of change in entropy for chamber 1 with respect to, again, the internal energy of chamber 1, the volume of chamber 1, and the number of moles of chamber 1. What we get then is that, and this is very fun. This expression here has 3 terms. This expression here has 3 terms. And this one here has 3 terms. Right, because we're going to take the partial of, let's see, there it goes here. The change in entropy with respect to internal energy, and then take that derivative again. Then take the change in entropy with respect to internal energy and volume. Then take the change in take the change in entropy with respect to change in number of moles, and then the change in internal energy. So this is going to be a second derivative, a second derivative, a second derivative. That's just this term. This one here, we repeat the process. ds, du, but then dv, ds, dv, then dv, ds, dn, then dn, and then we repeat the process a bunch of times over. Then we repeat all of that again for chamber 2. So, if you trust that the conclusion can be obtained, we can skip over all of the unpleasant math associated with it. And the 2 conclusions are relatively straightforward. Heat capacity always has to be greater than 0, right? This is a direct function of the stability criteria of the universe that we have derived through this simple system here. And recall that the heat capacity is a defined function. Right, we've defined heat capacity to be convenient. So all of the tabulated information that we have on C sub P or C sub V, we can show the same thing here as well. The whole purpose for defining these properties is what allows us to know what experimental measurements we actually have to go into the laboratory and make. So that's why we have these terms here. So this is always true. If you have a heat capacity that's negative, you're violating the stability criteria of entropy and the stability criteria of the universe. And it makes sort of intuitive sense as well, right? We know now that heat capacity, if we have some sort of a molecule, that corresponds to the bond vibrations, the molecule translations, the molecule rotations, right? That's how energy is stored in molecules. As we increase the temperature, what we're doing is we're activating more different ways that we can store the energy. At very, very, very low temperatures, molecules can really only translate through X, Y, and Z space. Activating the rotation is pretty simple to do. It doesn't take that much energy to activate a rotational mode in a molecule. But vibrational modes actually take quite a lot of energy. Even beyond that, there's electronic modes, right? You can have electrons jumping up into higher and lower energy levels. That takes an immense amount of energy. So one thing that's kind of convenient when you look at molecules from a molecular perspective is if you look at the electromagnetic spectrum. Down here on the very low, this is confusing, right? Typically you draw the electromagnetic spectrum the other way. On the high end, you've got kind of UV, you've got visible light, you've got infrared, and then down here you've got like microwave. So when we think about molecules and storing energy and thinking about heat capacity, it allows us to understand why certain spectroscopic techniques are used for different property measurements within a molecule. So who consider themselves familiar with spectroscopy? All right, we got one dedicated spectroscopist. What information does IR tell you about a molecule?
Vibrations.
Bingo. What does UV tell us about a molecule?
It's electronic.
So which of these two are higher energy photons?
UV.
Which means that it's harder to activate an electronic mode. So if you want to figure out the rotational properties of a molecule, you actually do microwave spectroscopy, but you've got to be super close to absolute zero. So if you can cool your compound down to a couple of Kelvin, you can shoot microwaves at it and you can determine how it absorbs the energy in terms of rotating the molecule, which is kind of cool. So with UV, right, that's where you're looking at the electronic structures, and UV is a very high energy photon, and you need a high energy photon to activate that energy mode. All right, so just a nice little relationship here, I think, to sort of spectroscopy for something that's a really very fundamental thing to understand. Because then when you're trying to think about a new compound or a new molecule and you're trying to figure out how to characterize it, just think, oh, what is the energy scale that I'm really interested in characterizing? That's the energy of radiation. I should shoot at it to see where it absorbs. Okay, that's just a little aside there. So this makes sense conceptually that we should never, ever, ever see heat capacity. Well, so first of all, that's a different topic. This is heat capacity should never be zero. Right? But in addition, you should never have the heat capacity go down as you increase it with temperature as well. Right? So there's a lot of cool kind of fundamental properties we can get out of this. The next fundamental result of this derivation that we skipped over is what we'll be talking about for a very long time. So if I look at the change in pressure with respect to the change in volume, it always has to be a negative slope. So let's take a moment and talk about this. So if I take the ideal gas law, and I calculate the change in pressure with respect to the change in volume at a constant temperature, again, I always have to rewrite this here. And then we take the derivative, so it's minus RT over V squared. Right? This is always going to be negative, which is good. The ideal gas law doesn't violate a fundamental stability criteria of entropy. We got lucky. So if we take a look at a plot of pressure versus the specific volume, which I always think of this as like the density, or it's the reciprocal of the density, but in my head, I just think density. The ideal gas law always looks something like that. If I shrink the volume of my system, my pressure has to go up. There has to be a reciprocal relationship between the pressure and the volume of a system. Always. If not, the universe is unstable. So that's where this criteria is derived from. Now what we'll be talking about is a class of equations called a cubic equation of state. Examples. What's an example of a cubic equation of state? Peng-Robinson is a great one. We have the van der Waals equation. We have the SRK. Those are the common ones. But there's a lot of other niche ones that are designed specifically for certain fluids. Like water, for example, might have a very dedicated cubic equation of state. Cubic equations of state are completely made up. But they are made up in a very, very convenient way. We call them cubic equations of state because at very low pressure or very high temperature conditions, they look like an ideal gas law. But they've got some extra unique features. Whereas you cool the system down or you pressurize it, a cubic equation of state will start to have some cubic function looking like characteristics. Now we'll go back to our stability criteria here. There are regions in the cubic equation of state that violate the fundamental stability criteria of real fluids. That region is bound where we have a positive slope in this curve of pressure versus volume. So if I draw a dashed line here, inside of this region, this is an unstable fluid, meaning it can't exist. Thermodynamics says it's not possible. So if you ever find a fluid that falls into a region with these characteristics that is predicted by a cubic equation of state, it basically says that can't exist. This dashed line is called the spinodal. The spinodal is a boundary that defines an unstable fluid. And it's commonly encountered in liquid-liquid equilibrium. Or it's the absolute limit of subcooling and superheating as well. Now what we're going to be talking about on Friday is how we can use the cubic equation of state to predict vapor-liquid phase equilibrium. There's another region that is bound by a cubic equation of state. And we'll talk about how we define this line called the binodal. This is the phase coexistence curve. So in a real system, the cubic equation of state just so happens to have a very useful functional form. It is, in fact, the simplest function that we can generate regions of unstable fluid and regions of pseudo-stable fluids. So we'll be showing that we can draw lines that kind of look like this, and I've really done a bad job here, and we'll see why next class. But basically, inside of this region bound by the binodal, or the phase coexistence curve, this is our multi-phase system that is in equilibrium. Up here, is this vapor or is this liquid? Vapor. We can double check it by a couple of ways. One, vapors tend to exist at low pressures, and vapors tend to have high densities. So this is going to be vapor. This region here, what phase am I in? Liquid. Low specific volumes or high densities and high pressures. What do we call this region up here?
Critical.
Supercritical. So this is the critical point. The critical point is when you first start to have the inflection that there might be an inkling or a hint that you're going to have a phase transition. So if I have a liquid, or let's try to think about it. Let's say I have a liquid and I'm heating it up, right? And I'm heating it up in an ultra super clean beaker in the laboratory. What's something that can happen when I heat a liquid in a super clean beaker?
It will not boil.
It won't boil. Why won't it boil? It eventually will boil, but for a while it won't. You can heat it up above 100 degrees Celsius, right? If I have liquid water, I can heat it up above 100 degrees because there's nowhere for the bubbles to nucleate.
Yeah.
Right? We'll be talking about that a little bit when we're talking about the phase, sort of the kinetics of phase transitions. But if I have a liquid and I'm heating it up, right, I can find myself in this area here, in between the binodal and the spinodal. The binodal curve, the phase coexistence says, you should phase transition, you should boil. But the cubic equation of state is still a stable fluid, right? It still has the right slope. It's still a negative slope. As soon as I hit this binodal, it transitions to an unstable fluid, and then it violently boils. So in chemistry class, or in chemistry lab, of course I was always bad at chemistry lab, you're supposed to put boiling chips inside of your glassware. Because presumably, if you're a good chemist, which of course I never was, if you're a good chemist, your glassware should be clean. There should be no dust, there should be no specks, there should be no nucleation sites. And so if you're trying to boil a fluid, well, that's going to be bad because it's not going to boil. And you're going to sprinkle a little chemical into your boiling water to do your nanoparticle synthesis, whatever the case is, and it's going to violently boil over, and your whole experiment's going to be ruined, and you're putting yourself in an unsafe condition. So the boiling chips that you add to a beaker or a test tube or whatever the case is in chemistry class, that's intended to avoid this fluid that wants to phase transition but is unfortunately stable still. As soon as you hit this region here within the spinodal, all of a sudden it becomes an unstable fluid where the curvature between pressure and volume is wrong, meaning that any slight change in the properties instantly causes it to vaporize. The exact same thing is true if you have, let's say, a beer and you put it into the freezer because you're really thirsty and you want a cold beer, but then you forget about it. And you take it out of the fridge or the freezer and you're like, oh great, I caught it in time. It hasn't frozen yet. And then you tap it and then the whole thing freezes. Same thing happens there again. You've created a mixture that is in sort of a metastable state. And then as soon as you give it a little bit of energy by tapping the bottle or opening it, being optimistic, thinking that you're going to get a drink out of it, the whole thing freezes up instantly. Because what you've done is you've given it just a little bit of energy to overcome this barrier to phase transitions called nucleation. And so I think in maybe a week or two we'll talk about nucleation, why superheating and subcooling occurs. But the cubic equation of state is useful because it is the simplest equation that demonstrates these real properties of fluids: superheating, subcooling, unstable fluids, and metastable fluids. And so what we do in these cubic equations of state is we basically take real property data information and we fit the coefficients in these equations so that it matches up with the regions that we see in the real fluid properties. Now the basis for these equations has truth in reality, right? They derive the equations based on their best representation of how they think fluids should occur, with concepts like the interaction parameters. They also have an excluded volume term accounting for the volume of the actual particles themselves. But in truth, these should be thought of as kind of semi-empirical relationships. They're useful because they happen to do relatively good predictions. But the utility of it all comes based on this stability criteria of the universe between pressure and volume, which all comes from the stability criteria of entropy. So to conclude another lecture, it all goes back to entropy. Okay. See you on Friday.